Okay, thanks everyone for coming today. So today we're happy to have Ryan Lanzetta, who will tell us about bootstrapping the magnetic line defect of the 3D Ising CFT. And take it away whenever you're ready.
Okay. Yeah, thanks, Justin, for having me come to talk today. Um, yeah, this is a project that I've been doing for a while with Zhang Liu and Max Militsky. It should finally appear soon. So, I mean, I've talked about this a few times over the past year or so. So maybe I hope it's not old for people, but yeah, it should finally come out soon. So, uh, I'm excited to talk about it now. Um, So the general plan will be that I'll just uh, talk about some basic background on conformal line defects, which will be the main thing that I'm going to try to develop some tools to study in this talk. We will then apply what we learn to the specific case of the 3D Ising CFT with its pinning field defect, which I'll explain what that is. And then I'll present the results of all this, the bootstrap bounds that I get, and then just say some concluding and remarks at the end for thinking about some future directions, hopefully. And yeah, I mean, I hope this can be kind of informal. So I mean, really, like anything that people are confused about or want more details about, really, you should just interrupt. I tried to make less slides than usual today, I think, just because I usually tend to go over, I think. So yeah, it'd be very nice if people have a lot of things to chime in with. Um, so, so the general subject is really line defects in quantum field theory. So these are kind of the simplest class of extended observables that you can construct in a given quantum field theory. And they describe many different kinds of physical objects in nature or theoretical settings. But a very concrete example is if I just have some kind of object like an impurity in a quantum material. So you can imagine I take some clean system, and at some location I add in some new degrees of freedom, like some different kind of spin or what have you. And I will try to couple this new degree of freedom into my original system in some way. And now the general question we want to ask really is if I do this, depending on what kind of couplings I make or what kind of new degrees of freedom I add, uh, what will happen at long distances? So depending on the type of defect I choose, it may or may not become some object that can be seen by the low energy degrees of freedom in the bulk CFT. And of course, it's much more interesting um, when the degrees of freedom in the bulk do detect this object, because then there will be some interesting things to study, which is the interplay between the bulk and the defect degrees of freedom. Um, so so this kind of process kind of sounded like adding some degrees of freedom. So we're taking a bulk system and then adding something new and asking what happens then. But we can also talk about removing degrees of freedom. And for this, you can kind of think about doing some kind of RG process. So so actually, the development of RG kind of was helped along by the study of defects when people like Wilson were trying to understand the Kondo problem, and indeed, like if I have a defect in some bulk, I can do RG on the bulk and defect degrees of freedom in a very analogous manner to how I do them when the bulk is clean and I'm just doing a normal kind of RG flow. And so this is the kind of setup that I'm going to want to try to understand in this talk, which is if I start from some fully clean system, like well, I'm going to be taking the bulk here to be described by conformal field theory. The setup I'm going to have in the UV is just no defect. Well, really, okay, I'm going to take a clean bulk and then add a relevant operator, but so deep in the UV, it still looks like a trivial defect, let's say. But and here relevant means that the scaling dimension of this bulk operator that I'm going to make this perturbation with will have scaling dimension less than 1. And so I'm going to take this UV setup, and then I'm going to do RG. And now I want to ask what happens in the IR. And so in the IR, what I'm going to assume is that the fixed point is what we'll call a defect conformal field theory. So a defect conformal field theory is a scenario in which the bulk conformal symmetry, which is SO, well, in general, it's SOD plus 1, comma 1 in Euclidean space. So this symmetry gets broken down to some subgroup, and usually it's natural to choose a subgroup where, well, to reflect basically the symmetry of the defect itself. So when I just have a line defect, I'll call something a defect conformal field theory when it preserves all of the conformal symmetry that preserves the location of the line.
One
So
silly question. Is your
sure.
theory reflection positive?
Yeah, so I'm gonna only talk about reflection positive theories here.
Is it
But this
easy to find operators with delta less than 1?
is it easy? Yeah, I mean, so like in the Ising CFT in 3D, there's
Oh yeah. Sorry. Yeah.
yeah, in 4D, I think it's much harder to construct uh line defects, at least perturbatively. So
Mm. I okay, maybe I'm really confused. What about, like, aren't there unitarity bounds that make these things hard to find? What are the unitarity bounds for like a scalar?
so for a scalar in D dimensions, it's D minus 2 over 2, right?
Uh-huh. Oh, okay. That's why you said it's going to be hard
Yeah.
for 4D. But I guess in 3D, you got a whole half a delta equals one half of wiggle room to find things
Right,
in.
exactly. Right. So in 3D,
Okay, cool.
in 3D, in any like normalizable theory, I guess, there should be probably some defects lying around, some operators lying around that you can uh, play with to
Hmm.
try to create some defects.
I see. Okay, cool. Sorry. Thank you.
Mhm.
And I guess in like ON models, this magnetic field gets pretty close to a half.
Yeah. Yeah, exactly. Um, yeah. So yeah, so so for a line defect, what I'm gonna really be assuming is that the symmetry that we have left over from the bulk symmetry is just the one-dimensional conformal subgroup, you could say. So it's just like this SL2R. And so this will contain the original scale transformations in addition to the translations and special conformal transformations that that are isometries of this line. And you can also throw in some of the transverse rotations and reflection symmetries that also preserve the defect, which we will do. But I think it's interesting probably in the future to explore defects which like break some of these symmetries, for instance. But I'm not going to do that here. Okay, so it's interesting that analogously to things like the C theorem in two-dimensional CFT or A theorem in 4D or whatever, um, there you can formalize this notion of adding and removing degrees of freedom by an interesting result that was properly proven only a few years ago. So this is going to be helpful for us to later talk about some of the observables that we're going to be putting bounds on. So the first observable that I'm going to introduce is this quantity called G. So the way we're going to define it is we're going to take some CFT and we can consider its SD partition function. So remember, we're going to be talking about D here is the space-time, Euclidean space-time dimension. And now we're going to measure the effect of adding the defect to the completely clean system. And we're going to measure this by like the free energy difference, you could say. So we take the ratio of these two partition functions, and then, okay, well, really, if we were to take the log of this quantity, we would be measuring like some kind of free energy difference. And this quantity is known as G. And so when we have a trivial defect, then obviously G is equal to 1 because we just have this sphere of partition function divided by itself. And then, so really we're going to be like measuring this G for different kinds of defects, and whether G is greater or less than 1 will roughly tell us like whether the defect adds or removes degrees of freedom in this localized way. And so just to reiterate just to mention what the theorem is now, the theorem is that if we start from some defect fixed point, which has, sorry, I'm going to turn my phone off. If we start from some defect fixed point that has some value of G, GUV, then we add an operator on the defect, which is relevant. And again, that means that the dimension is less than 1. That's this operator. I'll explain this notation more later. Then the statement is that the value of G in the IR fixed point is going to be strictly, or sorry, if this is a relevant operator, I think this should be really just strictly greater than. So, but yeah, it'll be the IR fixed point G will be less than the UV one.
Something.
Yeah.
So when big D is, I guess, even, no, odd, sorry.
Okay.
Then that's when the Euler characteristic of the sphere is 0, and that's when the undecorated sphere partition function has a meaning in terms of some kind of also RG monotone, I guess, in 3 dimensions.
Mm-hmm.
And I wonder, in that case, if you just, so I guess you do this dividing, so that counter term affects both of them.
True.
Equally, and there's no counter term. There's no extra counter term that you can write having this defect there.
The only other counter term, yeah, there is another counter term, but it's fixed. It's the cosmological constant counter term, but it's fixed by scale invariance. I mean, if you demand that you have a CFT, you say I just tune it away.
Okay, very cool. All right, thanks.
Yeah. Yeah, I don't know. Well, one silly thing I've wondered is like if there is some kind of like G plus F theorem in 3D.
Right, that would be so cool. Yeah, I
'Cause
thought about it a lot for boundaries too. Really interesting.
Yeah, because
But
like
go ahead, yeah.
well, yeah, it feels like if I just consider this guy, then
Sorry, I dropped you.
what's that?
I don't know if you heard anything, but I dropped you.
Oh, no,
I hope you're okay.
I'm okay.
Good.
Yeah, what I was saying is that it seems like if I just study this thing, like, and not divide out by the bulk, then like, I mean, there already is a monotonicity theorem for just this guy, right? So if I just add the defect, like, it seems like if I add the defect and do a bulk and defect RG flow, like, I don't know, it feels like there should still be some kind of result like this, which think would be pretty cool, but I don't
Right, I
know.
agree. Yeah, like maybe you can just show that that left thing is also an RG monotone.
Yeah, yeah, yeah. Yeah,
Yeah,
that's
cool.
that's what I would like. Yeah, I should try to think about that. Um, okay, anyway. So um so so yeah, so this G is a very simple kind of observable. Um and well, people are if you're familiar with like topological defects, then this G is also really the same thing as the quantum dimension of the topological defect. But we can also consider other kinds of observables. So, and in the rest of this talk, the thing I'll mostly uh, be working with will be these things called defect changing operators. So, so in a given theory, I may have many different types of defects, um, and I can consider a situation in which I join them together at a point. Um, and the and in general, this will create some non-trivial operator, which can be viewed as a conformal primary since it's well, it can be thought of as a creating an eigenstate of the dilatation operator. Um, and yeah, these objects are interesting to study. They can represent different kinds of things physically. You can kind of think of them, well, you can think of them in different ways. One way is if you think of like having a time direction going like this, then um, and you know, so at each slice, you have some Hamiltonian generating the time evolution, and uh, for time less than whatever we are here, the Hamiltonian will be having some fixed type of defect B, but then suddenly we'll quench this new defect type A, and and this process should create some kind of disturbance of the system, and that's measured by this defect changing operator. Um, you can also think of a picture where we have a sphere and we place two defects at the poles, and in this picture, the dimension of the defect operator of the defect changing operator, oh excuse me, uh, can be thought of as like the energy cost of creating this defect relative to having no defect. Because um, if I had no defect here and I considered the ground state of the system, then I would have uh, then I would have just scale. I would just have energy zero, which is fixed by the dimension of zero uh, of the defect. Of course, in even dimensions, there's a correction, but in 3D, it's just this. Um, and then yeah, and so, but well, it's kind of interesting that if I create two defects, it seems like then there's actually no cost. So it's kind of nice. Yeah, so okay, so these are defect changing operators. Um, so uh, so as I said, this setup where we we have a line defect when we make the line defect straight, then it preserves the most amount of the conformal symmetry, which is this SL2R. And as I've indicated, we can consider these defect changing primaries as being well, primary with respect to this SL2R. And so what we're going to try to do now is build correlation functions out of these defect changing operators and use this SL2R symmetry to constrain the properties of these correlation functions and learn some things about this different kinds of defects in general, hopefully. Um, and yeah, just to be, and so yeah, so we can consider objects like this where we place uh, different defect changing operators at different points, and yeah, we're gonna want to use all this SL2R structure to understand the correlation function. And yeah, just to be explicit, like in this work, I'm gonna really be taking the symmetry to be what I'll call SL plus or minus 2R, which is basically SL2R, where I allow determinant -1 matrices as well. And then O2T, which is the O2 group of transverse reflections and rotations. And the determinant -1 operators or transformations will be the ones which reflect the time coordinate, reflect this tau coordinate here. Yeah, and also you could consider defects that break any of these parity symmetries or anything, but which again I think that would be pretty interesting to study. But yeah, I mean a very concrete question like related to this is you can ask if there's like a parity breaking defect in the Ising CFT or something like that, because it would have to be non-perturbative because there's no parity breaking relevant defect operator in the bulk. But I couldn't find anything when I tried to do it. So
I was gonna say maybe this is exactly what you just said, but how would you even look for such a thing?
well, I mean the bootstrap equations that you set up are quite similar to the one that to the ones that well, I'm not going to be too explicit here, but the ones that you can write down for the Z2 breaking defect are pretty similar to the parity breaking defect, you could say. And so you just do kind of the same kind of scan and try to see if there's anything there. But I think
See if there's anything. Okay.
any outstanding looking features that could indicate some physical fixed point defect. But
Right.
yeah,
Makes sense.
I didn't say this too carefully though, so I mean
Mhm.
it's possible that such a thing exists, but probably who knows. Um yeah, so um yeah, so we're gonna study correlation functions of these defect changing operators uh well, just like normal local operators, these defect changing operators can have an OPE. So you can imagine that like if we take some small segment of the uh, well,
Can I go back to something you said? Is there
yeah,
a
sure.
different unitarity bound for parity odd operators?
Oh, in the bulk, yeah, I tried to. Yeah, that's a good question. Uh, I kind of thought that the answer is no, but maybe someone else knows better than I do. I don't. Yeah, um, yeah, like okay. Well, uh, I mean, driving the normal unitarity bounds, it mostly relies on well, yeah, it depends in some way on the spin. And well, for parity odd operators, there'll be some different tensor structures. So I guess in principle, there could be a difference, but I don't think I ever found when I looked this up, I don't think anyone ever mentioned such a difference. Uh, yeah, I don't know if anyone else knows better. Uh, but yeah, anyway, so the defect changing operators can have an OPE that looks pretty similar to normal operators, except that we have all these different defect labels that we need to keep track of. And so, well, the picture here is like uh, if I take some sequence of these defect changing operators, and then I take their OPE, then when I zoom out, this should well, let's call this C actually. When I zoom out, this should be some superposition of defect changing operators that, well, this doesn't need to be primary or anything. So this will be some superposition of defect changing operators that interpolate between the defects C and A. So we can write down a pretty standard looking OPE for these defect operators in the limit where the defect is kept perfectly straight. And the usual constraints on like OPE coefficients of the descendants of these different defect SL2R primaries. The same constraints that apply for these descendant OPE coefficients for any SL2R symmetric OPE apply here. And so in the end, we will be able to take 4-point functions of the defects of these defect changing operators and expand them into conformal blocks, sorry, into some sum over the SL2R conformal blocks weighted by different contributions from the OPE coefficients of different defect changing operators with other ones. So, and so then depending on what kind of defects we choose for each of these operators, so we can consider if we start from some set of defect changing operators and look at all the correlation functions we can generate out of these, then all these different choices will have very different operators appearing in the internal channel, and I'll spell this out a little more in a bit. But so well, an interesting thing is how this the defect G function appears. So so if you think about using the OPE to solve these different correlation functions, whenever we let's say we have 4 operators and then we take the OPE a bunch of times, and then ultimately this will just be the expectation value of the identity weighted by all these different contributions from all these operators. If the defect type that we have at infinity is non-trivial, then the expectation value of the identity operator in the presence of some defect, which I'll call like this, will be equal to G. But what we're gonna do is choose some normalization for all of the defect changing operators that makes their 2-point functions be just 1 over some power law. And then when you do this, you find that the G function will appear in this way as the coefficient of the identity conformal block, which in this case is just 1. And so the fact that this G function appears in this way will be what allows us to actually put bounds on it. So, so the 4-point functions are subject to crossing symmetry. And you can think of this, actually, I think I wanted to, did I? Oh yeah, I sort of wanted to make some comment, actually, because one thing that comes up in some of the literature is a subtlety related to well, really like what it means to have a straight infinite defect and whether you can really define G using a straight infinite defect. And the subtlety is really related to the choice of whether you want to allow special conformal transformations to be a good symmetry or not. So, so I'm going to say that special conformal transformations are a symmetry. And what that really means is I think I'm taking my infinite straight defect to really be a limit where I have a circular defect and I take the radius to be extremely large. But if you genuinely have a straight infinite defect where the points at plus and minus infinity are not identified, then you can compute some different value for G. And so we should think of all correlation functions involving these defect changing operators as being regulated in this way. So that's what I'm going to do here.
Does that mean the conformal groups in this case is disconnected?
When you think of like RD, basically when you think of R as the space-time being like RD, not RD with the infinity.
Oh yeah, I'm just confused what you said. So you can leave out special conformal transformations. Um, but then what do you get? You just get rotations and scaling or something.
Yeah, and translations.
Yes,
Yeah, then it doesn't sound like the conformal group. It just sounds like Poincare with scale symmetry, right?
that's right. Yeah.
Right, but well, yeah, but it's like I mean, the underlying theory still has the symmetry that would make it so that if I put it on a manifold that respected conformal symmetry,
No, I see. You're saying, does putting in the line defect preserve the K inside SL2R or not?
it's really does like I think the question is the same as saying does RD respect conformal symmetry? Um, so like what happens to zero under an inversion? It gets mapped like
Right. Hmm.
I think
Yeah.
that I think it's just like the RD doesn't like the special conformal transformation isn't really a well-defined map, I guess, on RD.
Maybe another way to say it is you're saying whether or not you consider RD or its conformal compactification, which is just adding the point at infinity or not.
Right, yeah,
Is that?
exactly. Yeah. I just want to add the
Yeah.
point of infinity, yeah. But then I think it's more like just SD with like a very large radius or something like that. Uh, yeah, so it's like, yeah, basically. So yeah, the point in the end is just that I want to always be regulating the defect in the IR as a being circular. But
But
then
then,
like
sorry, a physical comment. You mentioned that what you get for G is different in these two cases.
yeah.
And so, like, numerically, which one matches experiments? Does it differ? Like, does sometimes an experiment looks like it's on RD and another time it looks like it's on SD, or?
Yeah, I don't know if this has ever been measured in experiment, but like the I mean, yeah, the weirdness is the following. So like I think in some I can look up the paper, but it's a paper by Drucker. There's others
Hmm?
from some other authors, and like so they explicitly compute in some gauge theory that like probably I don't know some n equals 4 super Yang knows probably like some Wilson loop when it's circular, and then they compute it when it's straight and infinite. Um, and when it's straight and infinite, there's a symmetry that causes a bunch of diagrams to cancel, and they just get G equals 1 for this defect, I think. But then for the circular one, they get something else. And like, and so, but the straight line and the circle should be related by a conformal transformation. But I think like if you explicitly like uh if I have some explicit Lagrangian and I just like create this defect in a conventional way by integrating some thing like a gauge field or whatever to create a Wilson line, then probably that looks more like the straight defect. But like, um, but the thing that I'm going to compare to in Bootstrap is always going to be the circular defect, because yeah, I'm going to demand that this special conformal symmetry is respected. But yeah, it's a little bit confusing.
But then one thing people usually compute is like bulk correlators, maybe in the presence of the defect or something like that. And then in that case, since you just normalize always by the correlation function with just the defect, I guess then that those computations are invisible to this subtlety of Drucker at all.
Yeah. If I
I see.
only have, yeah, exactly. Yeah. So yeah, so there's some crossing symmetry here that we can kind of think of as coming from this circular regularization at infinity, where we always have this freedom to map points to we always have this choice of mapping 3 points to a fixed set of other 3 points, and we can do this in different ways. And one of these looks just like basically permuting the points that we insert all these defect changing operators on the circle. So now the thing we're going to want to do in Bootstrap is use this crossing symmetry, choose some set of operators to impose these relations on, and then study the constraints that we get on different aspects of the CFT data that enter the game. Okay, so yeah, so let's now focus on the case that I studied in this project, which is just the 3D Ising CFT, and what we're going to introduce as the pinning field defect. So just recall that the 3D Ising CFT has a number of important distinguishing features. Well, mainly it has a Z2 symmetry, and it has two relevant operators. So it has sigma and it has epsilon. Epsilon represents the thermal perturbation, which drives the transition drives the ordering transition, and sigma is the order parameter. So at this point, much is known about 3D Ising CFT from many past conformal bootstrap works. Yeah, I haven't been very good about providing references, but these are by now pretty well known. And so really, like, the work that we're gonna do in this project to try to understand the defect is gonna really essentially rely on all this stuff that's known in such a detailed way about 3D Ising bulk. So we're going to use all sorts of things, including the scaling dimensions of these leading operators, as well as a bunch of stuff that comes from the higher energy or higher operator dimension sectors of the Ising CFT. So yeah, all of this data is going to be very important in us being able to try to study this particular line defect that we're going to look at. And so now what we're going to do is start from the 3D Ising CFT in the bulk, and then make this specific perturbation where we integrate the sigma operator along a line. And now what we want to do is understand the IR fixed point of this defect that we create. So because sigma is odd under the Z2 symmetry, the line that we get in the end will not respect the Z2 symmetry. So we're going to have this defect, which I'll call D plus or minus, depending on what sign we chose for H. And the plus defect will get mapped to the minus defect under a Z2 transformation. So I will say that, like, this is a pretty old problem. I think it was first studied by Elise and Sachdev like 10 years ago now. And then since then, there's been a number of follow-ups using a number of different techniques, Monte Carlo, perturbative calculations, various others. But like, yeah, in the end, what I'll mostly be comparing to is the most recent numerical calculations from fuzzy sphere, which seem to be extremely accurate. And what we'll see is that they also agree very well with what we found from Bootstrap. Okay, so now if we want to try to bootstrap this defect, we should think about how to construct this fixed point from the bottom up. So we need to think about what kinds of properties do we expect this defect to have that are that are guaranteed in some sense. So as I mentioned, the defect is going to break the Z2 symmetry. Second, we're going to assume that the defect is endable. So what that means is that I can consider a scenario where I've only turned on the defect in part of space and everything else is just left as the trivial defect. This is not general. For instance, if I have a one-form symmetry, that if I have some line defect that's charged under one-form symmetry, then the defect won't be endable, or there's some geometric reason why the defect can't be endable, like it's attached to a topological surface or something like that, which is, well, ultimately is kind of the same reason as having one-form symmetry, but again, that kind of defect, the things I'll say here won't be quite as effective to study those kinds of defects, but luckily for us, we have this endable defect, so we're going to assume. Okay, third, we have an IR fixed point, and really there's no other symmetries we want to preserve other than like, okay, maybe parity or reflection or something like that, but so there's really no other symmetry constraints, and so since we have this IR fixed point, what we're really going to do is assume that all the non-trivial defects, genuine defect operators have dimension greater than or equal to 1. So this will be one of the things that we explicitly assume. And then finally, from the G theorem, we expect that these pinning field defects have G less than 1. Since we start from the trivial defect and do some defect RG flow. So this should be something that we expect to see, and this will be something really that we don't assume, but we look for in our bounds, and then based on the regions where this G is less than 1, that's where we'll look for to try to find out what's the location of the real physical IR fixed point that we're trying to study. Yeah, so now the question for Bootstrap is, if we make all these assumptions and we assume that we assume various things about the 3D Ising bulk, what scenarios of the defect CFT data are going to be consistent with all these assumptions? So we're going to look to bound like all these different quantities, like G, scaling dimensions of different defect changing operators, and so on. But like, well, I do want to just introduce this more physical problem beyond like the technical challenge of just trying to find all these numbers, where we are able to more accurately construct this defect, which is this question of whether you can have ordering of a Z2 symmetry on a line if I embed the line in some higher dimensional bulk gapless system, like a CFT. And for this, we're going to want to try to understand this superposition defect, which is if I take the plus and the minus defect and take their direct sum. So you can think of constructing this kind of defect just from these building blocks in field theory as coupling some qubit, which is made dynamical to the sign of the perturbation that we make to make this pinning field defect. But if you're like a lattice person, I think it's also a nice picture to have, which is if we take the let's say we take the critical transverse field, some critical transverse Ising model, and we completely turn off the spin flip coupling at some site by just subtracting the poly X operator at that site. This will make the Z operator at that site commute with the Hamiltonian and will guarantee a twofold degeneracy. And we should really think of this. So now it's like, we can explicitly break the symmetry and go into some pinning field situation, or we can try to like force order on the defect by making the term which would flip the spin and again like destabilize this whatever defect we have that's representing the ordered phase. We're in the bulk, if we turn off X everywhere, then we would flow into the ordered phase. So we just do it only on the defect. And so now the question is like, if we started this defect where X is exactly 0 at some site, and then reintroduce X weakly, only allow a small X perturbation. We're going to try to argue that this defect fixed point is unstable based on whether this small X perturbation destabilizes this X equals 0 fixed point. So at long distances, if it looks like there's some flow towards probably a trivial defect or something like that, then we would say that this fixed point is unstable. And this question is going to be exactly related to, in field theory, what's the scaling dimension of these domain wall operators? So we can take a plus defect and join it with the minus defect, and this represents a domain wall operator when we explicitly, like by hand, put in these two pinning field defects. But these domain wall operators are local operators at this direct sum fixed point, as we can see here. But the local operator corresponding to the domain wall is just X. And so the stability question is really related to the dimension of this domain wall. And so we're going to try to put some bounds on that. Okay, so to bootstrap this defect, what we're going to do is incorporate a lot of information about the bulk. We're going to this is going to enter because when we take a small segment of the defect, we expect that it can be expanded into bulk operators. And so in particular, this means that since we know so many of the bulk operators, we can directly assume what values of scaling dimensions appearing in this bulk channel are allowed for up to some cutoff that we'll choose. But of course, also the endpoint operators can be fused into genuine defect operators. And the interesting thing to note is that these two different expansions are related by crossing symmetry. So if I consider this channel where I would take the OPE of here and here, then I would have an expansion into conformal blocks where the internal exchanged operators are bulk. But if I were to do the expansions here and here instead, which is related by a crossing symmetry transformation, then I would be expanding into defect operators. And now, if you recall, in this channel, we're going to have a non-trivial factor of G because the defects at infinity are non-trivial. But in this channel, we don't have a factor of G because it's just the trivial defect. And so in these kinds of crossing equations, we're going to be sensitive to the value of G because the identity operator over here is going to contribute with a different prefactor than it is over here. So we can't just like scale out G from the whole problem and forget about it. So what we need to do basically is enumerate all possible correlation functions, and we're going to choose a bunch of different external operators. So we're going to choose the endpoint operators and sigma and epsilon, and then we just need to enumerate all possible correlation functions involving them. So we can consider different cases where we have like endpoints corresponding to all the plus defects, or we can have two endpoints with a plus defect and two endpoints with a minus defect. And this would have some expansions in terms of domain wall operators. And we can also consider correlation functions of the endpoints with bulk operators. Okay, so we just have to enumerate all the possibilities. But no matter what we do, we're always going to consider the operators, even when they're just in the bulk, as being in the collinear limit. So we're always gonna have, if we have some defect and we have some bulk operator insertions, we're always going to make sure everything's in a straight line. And again, this is just to preserve the SL2R symmetry. So yeah, so I'll try to mention quickly some ways to be sensitive to the fact that these operators are actually 3D bulk primary operators. Um, but well, yeah, I'll just do that now quickly. So yeah, for these bulk operators, basically so far everything I've said just treats them as SL2R primaries. But we should also remember that they're primaries under the under the bulk conformal symmetry. And so what we're going to want to make note of is, like, let's say we have some bulk primary O. We can organize its conformal tower into operators that are primary under the SL2R. So that'll be these guys. And now the interesting thing that happens is when the OPE of the endpoint operators contains this bulk operator, the OPE coefficients of this O and all of its descendants, which are SL2R primaries, in principle are independent. Because these guys will contain some transverse derivatives, which is part of the broken conformal subgroup. And so at least not obviously there's not an obvious way to fix these different OPE coefficients. Although I think, well, it seems like something that's worth thinking about, whether there actually is some way that could be kind of non-trivial in order to fix these OPE coefficients. But yeah, I haven't been able to figure out how that's possible. But then for when this O appears in the OPE of bulk operators, all of these descendants will have their OPE coefficients fixed by the bulk conformal symmetry. So we'll have a bunch of different ratios of OPE coefficients that are going to be now known. And so something that we do is incorporate these different relations into the Bootstrap setup. And yeah, I mean, if people are curious after, we can talk about that. Okay, so let's talk about some results that we get out of all this. So first, what we're going to derive is some very universal bounds on the two most important quantities I'd say that we're going to study, which is the G function and the scaling dimension of the lightest domain wall operator. So for this calculation, very little goes in. So we're really just looking at the most simple system of correlators, which is just two segments of defect with both the plus sign, and then the next one is I have a segment of defect with the plus sign and a segment of defect with the minus sign. And so these two correlators will both have expansions into bulk operators, and then they'll have expansions into domain wall operators and genuine defect operators.
Can you remind me how you get G from a correlation function? Is it this short segment?
It's like it's the, well, I guess it's like it contributes to the identity contribution to the conformal to the 4-point function, like here. Is that what you mean, or do you want something else?
Is that from just like two defect changing operators? So like a little short segment and what that projects onto the identity operator?
Oh, so it would more like be if I have two long segments of defect and then I fuse them onto the identity operator. So it's like this is like dividing by the norm of the identity operator, basically. Like, so when I
Solid defect.
Yeah. Mhm. Yeah, so so here we have some bounds on G that are very universal. So there's essentially the only assumptions I'm making are just that, well, I have any bulk, and then I'm gonna vary the dimensions of the bulk by tuning the unitarity bound that I set for all the bulk operators when they appear in the expansion of defect operator the endpoint operators. And then the first calculation is to compute G as a function of the dimension of this endpoint operator. And well, actually, I think it's kind of nice to interpret this plot when you rotate it by 90 degrees and think of it as a lower bound on G as a function. Well, sorry. Yeah, sorry. As a function of G, think of it as a lower bound on the dimension of the endpoint operator. And so, well, maybe I'll just explicitly. Okay, wait. Can I rotate it? Maybe not. Anyway, well, so if you think of it as a lower bound on the endpoint dimension as a function of G, then we see that like in higher dimensions, if you sorry, in higher dimensions, if you add degrees of freedom by making G positive, then it will necessarily cost some energy. If you think of the dimension of the endpoint as being like this energy on a sphere of creating this defect. And similarly, if I remove degrees of freedom, then again, there'll be some lower bound on the energy that I'm required to add to create the defect. And this bound seems to get lower when I decrease the dimension. And in 2D, apparently, I wasn't able to derive any bound. But yeah, I think that's kind of nice. It again kind of gives some intuition for kind of like the G theorem, I'd say.
This is like a random question, but is this if G is very, very large, is there some like remnants of like black hole entropy formulas showing up?
Mm. I have no idea.
It's sort of telling me there's a relationship between like the entropy of the defect and its energy, right? Its mass.
Yeah, that is true. Yeah. I don't know. I mean, yeah, I don't really know anything about black holes, so, but that could be cool, I guess.
Yeah, me neither. But I guess some of these large C stuff are related to like weak gravity conjectures.
Uh-huh.
Things about the twist gap and so on. But I don't know anything about this G.
Right, right. Yeah, I don't know. That yeah, that could be cool. But yeah, oops, I moved this thing. Okay. So yeah, so then okay, we can also do this very universal bound on the dimension of the domain wall operator, and yeah, so with very little work, we can get these universal bounds again, and well, yeah, like in 4D, we see that the bound is basically saturated by a free scalar, and well, I should mention that in both of these plots, I've compared the corresponding computations in Ising CFT in different dimensions, but the islands here are coming from the bootstrap calculation, but the 2D Ising islands are exact. And so yeah, so here we have one result here is just that we have some universal lower bound on what the dimension of the endpoint must be in order for the domain wall to be irrelevant. So in other words, for this non-simple defect to be stable to the domain wall. So so yeah, so then we can compute some other things. So one quantity that is it's not like the most physically important perhaps, but it kind of encodes a useful piece of information for Bootstrap is this ratio of OPE coefficients of sigma and epsilon appearing in the OPE of the endpoints. So so it turns out that in Bootstrap, like if you fix some ratio of OPE coefficients, then it's analogous to basically saying that there's only one OPE channel where operators of that dimension contribute. And so it kind of encodes the uniqueness of these operators. So so we encode this. So we can do this calculation and get these very, in the end, once we make some stronger gap assumptions, we can get some very precise estimates for the size of the island that the dimension of the endpoint must take, and also this OPE ratio. And yeah, this is essentially just going to be some new input that we put in the later calculations to make the bound stronger. But you know, it's still interesting physically. But yeah, I guess one thing to point out is also, like, you know, we have this island where it's extremely likely that the physical value of all the physical pinning field defect quantities live in this island. It satisfies all of our constraints, as we'll see later. But there's also this other region which is not ruled out. But there's no real features in this other region that we could see, so it's kind of unfortunate. But it's something it's interesting to point out. But yeah, it's also, I guess it's also good to say that, like, the fuzzy sphere estimate for this quantity is extremely close to what we found here, so that's nice. Yeah, and then we can just go through and, well, I'm kind of over time, so I'll just go through this quickly. But yeah, so we can just go through and compute other things like the dimensions of all these different defect changing operators. And the general theme is that, like, where the bound appears to be very insensitive to increases in the precision, like the number of derivatives we take of the crossing equation, this appears to coincide very well with where the fuzzy sphere predicts the value of these quantities to be. So that's a very good sign. And then and now let's compute finally the G function. So the most significant point of this plot is that even on this biggest island where we make only the most general assumptions about the defect, only the ones I outlined on the slide previously, there's no other non-trivial gap assumptions that we make. We always find that G is less than 1, which is what we expect. So this is good evidence that very likely the defect lies somewhere, the true physical value of the defect lies somewhere on this plot. And then what we can also see is that if we make the assumptions much stronger, you know, ultimately we decided based on, like, existing numerics and other things, like, where to stop. But pretty much no matter what we choose, there's some little patch here which really doesn't seem to care at all about the choice that we make for these other gaps. So this is, again, very nice evidence, I think, that we've really hit on the true value of the defect. We can continue, and I mean, pretty much we already knew. Well, we didn't quite already know, but, like, well, now we know. Well, sorry, we did know from this. Actually, I forgot to say that, like, wherever the actual 3D Ising pinning field defect lives on this island, here I've only plotted the range, like, where this island is essentially. And yeah, no matter where we are, the domain wall operator is always relevant. So this is a very nice result, I think, about the pinning field defect of the Ising CFT, which is that this domain wall is always relevant. Yeah, and then so yeah, we can just again make these stronger assumptions, and we can get some more accurate prediction for what the actual domain wall dimension should be. Yeah, and these are, like, the final like most precise islands that we would want to present that we have here. Yeah, a fun one. It's kind of like, okay, probably getting, well, a fun one is the stress tensor OPE coefficient with the it's this ratio of the stress tensor OPE coefficient appearing in the endpoint OPE with compared to the OPE coefficient of T appearing in the sigma OPE. So if you think of the 3-point function of T, where you, like, you know, always I've been taking the T to be inserted parallel to the defect, let's say. But if I were to take the T off of this axis, then this should have some theta dependence as I approach the defect. But the integral of t around some spherical shell containing the defect should, by the word identities, give me the scaling dimension, should measure the scaling dimension exactly of the defect. And so, but also, like, when I approach the defect, I generally would probably expect some divergences to appear. I would probably, there would be some divergence as the t approaches this defect, and some part of this divergence would be subtracted off, which doesn't actually contribute to the word identity, um, but yeah, in general, I would expect some other contribution occurring from bringing the t near the defect. But in the end, I still have to recover the scaling dimension of phi. And so the expectation is that the 3-point function of phi with t should be lower than what it would be if these operators were just standard local operators. And indeed, if we think about the ratio of these OPE coefficients, what they should really give if they were just local operators would be like delta phi 0 plus by delta sigma. And if we know that the dimension of delta phi 0 plus is like about 0.1, then we would expect this to be like 0.2, since the dimension of delta sigma is like a half. But we found it to be like 0.1 again. So this kind of confirms this intuition that the consistency with the word identity should probably indicate that this value should be less than 1, or less than what it should be for a local operator. So I think that's kind of nice. Okay, so just some simple final remarks. Just yeah, so I think this program, I think of using endpoints in Bootstrap to try to understand line defects is, I think seems like pretty successful. And I think, like, yeah, there's various other interesting cases where I think this can be developed further, like, and I think the main thing I see in the future that would be cool is if if there's some, well, apparently it seems like there are some difficulties in using Bootstrap to understand 3D gauge theories, or really like the conformal fixed points associated with gauge theories and plus matter in the IR, let's say gauge matter theories, then well, it seems like a part of the story could be like things like Wilson lines in these theories. And what I think I've shown here is that when you have some endable line defects, they can be treated on the same footing kind of as local operators. And so yeah, it seems like hopeful to think that if you extend this program to these kinds of cases, that some more progress would be able to be made, even maybe on just trying to understand the bulk itself. So yeah, so I'll just leave it at there, and yeah, people want to keep chatting or something, that's cool. But yeah.
Okay, well, thank you. Thanks for the talk. Are there any people who want to make on record questions or requests? Because I've got some questions, but can save them. All right, I'll stop the recording.